In this video, we're going to see how to find the derivatives of inverse functions. So, first off, the formula for finding the derivative of an inverse function is this. The derivative with respect to x of the inverse function of f will be 1 over the derivative of f evaluated at the value of the inverse function. And this can be a little bit confusing for a couple of reasons. First, how do we do it? And second, why do we do it? So let me start off with giving sort of the steps that I like to go through. The first thing that I always look at is I try to find the input for the original function. So that's this part right here. The output of the inverse is the input for the original function, and I usually actually try to think of it in this context. It makes it easier for me to actually find what I'm looking for. The second thing we do is evaluate the derivative of the original at that value. And finally, the third thing we do is we find its reciprocal. Now, in the next two slides, I'm going to show a proof and show the rationale behind it so you can understand better what's going on. If you'd like to, there are links to the times in the description, and you can skip straight down to the first example if you would like. But onward, so a proof of this. So for this proof, I'm going to say, all right, let's let y equal f inverse of x. And before I know this formula, I have to do this in some other way, and so if y is f inverse of x, that means that f of y is equal to x. Inverses flip the inputs and the outputs. There was a question in class about this, so a little explanation for that portion of it is something like this. If y is equal to the third root of x, if I cube both sides, that means y cubed is equal to x. That's what's going on. I'm sort of flipping the function with its inverse. Now, on this point, or at this point, I'm going to take the implicit derivative of both sides with respect to x. And that will give me f prime of y. And since this y isn't an x, I multiply that by dy dx. And the derivative of x with respect to x is just 1. Solving this for dy dx, I get dy dx equals 1 over f prime of y. And dy dx, the derivative of y with respect to x, is just the derivative with respect to x of f inverse of x. And this y here is just f inverse of x, and so we get 1 over f prime of f inverse of x. And so that's a quick proof. So at this point you might say, okay, I can sort of follow along with the steps you're doing, but what the heck just happened? Why do we end up with this? So the proof shows why it has to be true. Now let's see about why it makes sense for it to be true. So consider a function. So I'll draw some axes, and I will draw an original function here, so sort of like an exponential. So this will be my f function. And let me draw its inverse. And remember, inverses switch inputs and outputs. So if this point 0, and let's say that's 0, 1, is on the original, then the point 1, 0 will be on my inverse. And if this point, like, let's say -3, I don't know, 1/3 is on the original, then 1/3 -3 will be on my derivative, and I'll get a function that looks like this. Also, graphically, it is reflected over the identity line, y equals x. And here's what happens. If I have a point here on the original function with some tangent slope here, this point corresponds to a point on the inverse with a tangent line that just flips the x and the y. So you can see it makes sense that, okay, I have these points that correspond. They're the specific points where if I take these coordinates and flip them, I get the other one. That's how inverses work. I'll label this as f inverse of x. And if I flip the x and y, I will find the reciprocal of the slopes. It's not perpendicular, it's not opposite reciprocal, it just is the reciprocal. So that's a little rationale as for why it would make sense. Now let's see two examples. The first example is this. I want to find the equation of a line tangent to the inverse of this. So for tangent, first off, I always start off by finding the point. And hey, they give me the point. So that's old stuff. Now the new stuff, slope. And I'll go step by step. The first step is finding the input for, in this case, the f function. And since -1, 2 is on y equals f inverse of x, where -1 would be the input for the inverse and 2 would be the output, this means that 2 is the input for f. So I'm going to use the 2. Second thing, I'm going to find f prime of this 2. So f prime of x is going to be 3x squared minus 6x plus 1. F prime of 2 then will be 3 times 2 squared minus 6 times 2 plus 1. 2 squared is 4, times 3 is 12. -6 times 2 is -12, plus 1 is 1. And I guess this isn't a great example because I'm going to find the reciprocal of this. That's not how you spell reciprocal at all. Let me actually do that correctly. So I will just flip this and get 1 over 1, which is still 1. So this will be the slope. Let me unbox that. That's my final answer. And all of this taken together gives me my tangent line, y equals 1, x plus 1 plus 2. So if they give you this information and I can figure out which x to put into the derivative of f, super easy. What happens if they don't give you that information? What if they give you this? So I do the same thing. Now, I don't need to find the point. I don't need to find the tangent equation. I just need to evaluate the derivative. And so I'll start in the same process. So first I need to find the input. So if 3 pi minus 2 over 2 is the input for G inverse, then that means it is the output for G. And so what I'll do is I will set G equal to 3 pi minus 2 over 2. Now, depending on the equation here, depending on the resources you have, I could try to solve this algebraically. And in this one, I don't have a great method to do it. If this were, instead of minus 2 over 2, let me put to the side here, if this were 3 pi, right, actually this will work, okay. Sorry, let me ignore that, got off track. So, I'm going to show you the calculator method first, but because of how I know this function behaves, because I've seen it often enough, I could actually mental math this problem. But let me jump into the calculator. So what I would recommend doing is graph this, and see where they intersect. That's always an option for us when we are evaluating, solving equations, and I just need a numerical solution. So I will graph 3 pi minus 2 all divided by 2. So 3 pi minus 2 all over 2. I will graph sine of x plus x. So sine x plus x. And that's going to tell me that my solution will be here. So let me second calculate, intersect, and I'll actually go over this way. Again, you press left and right to go along, you press up and down to switch curves. So I'll go over until I'm close. Not really necessary for this problem, but I'll do it. Press enter for the first curve. Second curve is sine of x plus x. Press enter. My guess, I think that's pretty close to where they intersect. And so I will get 4.71239. So x is approximately 4.71239. And I'm keeping extra decimals here because if I want to do this numerically for AP and I want to round to 3 decimal places at the end, I'll keep extra decimals until I round at the end. It'd be better to keep all the decimal places, but keeping 5 or 6 is usually good enough. Now, I actually know a little more about this, so here's a little aside. Because I have seen this function enough, I know that the sine of 3 pi over 2 is -1, and so the sine of 3 pi over 2 plus 3 pi over 2 will equal -1 plus 3 pi over 2, which is this. So I do know that it will actually be exactly 3 pi over 2. And let me go back to the calculator to support that. So if I quit out here and just do 3 pi over 2, you see the same answer, 4.71239. So I'll use this value, but if I'm allowing for the decimal, both will work. Now, what do we do? Okay, so we have our x value. Second thing we do is find the derivative, so g prime of x is going to be cosine of x plus 1. And so I'll evaluate not the inverse, the derivative of my input for g, which is going to be 3 pi over 2. And again, numerically, I could use that if I have the calculator. And so that's going to be the cosine of 3 pi over 2 plus 1, which is also equal to 1. And I guess I made a dumb mistake. I didn't show different things here. So find the reciprocal of 1. 1 over 1 is still 1, and that will be the derivative of the inverse of g evaluated at this x value. Alright, I hope this helped out. Feel free to comment below if you have any questions. If I get a chance, I might come back and fix this somewhat so that I don't always have the derivative of the original and the inverse both being 1. It doesn't quite show it. As a sort of a side to this, if this had equaled something like 3, then the derivative of the inverse would be 1/3. If it had equaled something like -2/5, the derivative of the inverse would be -5/2. So, of course, those weren't the problems I made, because I was a fool when I made them. I didn't double check that something more interesting happened. But just as a sort of reminder, if you have questions or if you want me to make more examples where these aren't one, feel free to comment below.